Want to do a speaker check?
Sure thing.
Good to see you, Dan.
Great to see you. Absolutely.
I'm going to make a real short introduction for you, and then you'll get started. But you're sounding real good, so I think we're all set.
Great.
Okay. They told us to get back at 10:30. So I'm going to ask Aubrey to signal me when I should get started.
Let's just give a minute, Robert, and let everyone to kind of settle
Thanks,
back
Sally.
in. So thank you though, Robert.
Okay, I'll start in 1 minute.
Yeah, perfect. That way everyone can sit back down and we're doing really good on time. So I'd say that would queue up to do well.
Okay. I think we're going to get started with our second speaker. It is my pleasure to introduce Dr. Daniel Sanchez, who is an assistant cooperative extension specialist at University of California, Berkeley. Still early in his career, relatively speaking, I should say. Dan is already recognized as a leader in the field of carbon removal. In the past 5 years, he has published impactful assessments of carbon removal in Science, Nature Energy, Nature Climate Change, Nature Sustainability, and the Proceedings of the National Academies of Science, among other leading journals. He runs the Carbon Removal Lab at UC Berkeley, which aims to commercialize sustainable negative emissions technologies and supports outreach to policymakers and technologists in California and across the United States. Prior to joining the faculty of UC Berkeley, Daniel was an AAS Congressional Science and Engineering Fellow. He has previously held positions with the Advanced Research Projects Agency Energy, ARPA-E as it's known, Green for All, and the California Public Utilities Commission. He holds a PhD and MS from UC Berkeley's Energy and Resources Group and a BSc in Chemical and Biomolecular Engineering from the University of Pennsylvania. Dan, we're glad to have you join us today.
Thank you so much, Robert. It's a real pleasure to be here. And I have a really outstanding opportunity this morning to talk to all of you about emerging engineered carbon dioxide removal technologies. So let me go ahead and share my screen and get started with the presentation. Excellent. So I'm going to be talking today again about engineered carbon dioxide removal in the United States. And this is a new and emerging suite of technologies that we think have a tremendous opportunity to remove carbon dioxide from the atmosphere and reliably store it out of the atmosphere for decades, centuries, or millennia. But again, we're in the pretty early stages here, and I'm going to talk about 3 specific technologies today that I think are particularly promising and particularly interesting in the engineered carbon removal space. So I'd like to think about carbon removal as proceeding through 2 broad classes of technology. One of those, which you heard Dr. Robertson just speak about, has to do with using biology to remove CO2 from the air. It's typically involved with the management of ecosystems, and land is typically involved. This can be the restoration and management of terrestrial land or of aquatic ecosystems. it could involve changes to our farming practices to store more carbon in soils. Moving to the right, however, there are a range of what we call engineered carbon removal technologies. And rather than relying solely on biology, these approaches typically leverage chemistry and other industrial processes to remove CO2 reliably from the air. The three most promising and most leading forms of these technologies include direct air capture of CO2 directly from the atmosphere, the enhanced weathering of minerals and carbonates that are naturally occurring in geologic formations, as well as the production of energy or other products from biomass, coupled with some kind of long-lived carbon storage. In this case, it's shown here as bioenergy with carbon capture and storage. And just to draw some clear distinctions between these biological or terrestrial approaches and these engineered or industrial approaches, I want to direct you to the bottom of this figure. The biological approaches, in many ways, you're leveraging photosynthesis, you're leveraging natural processes. So these are approaches that are less costly, they're closer to deployment, but they're also, as discussed previously, more vulnerable to reversal. And they typically bring environmental co-benefits, though. In contrast, the engineered approaches like direct air capture tend to be more costly. They're in greater need of research and development, but they are less vulnerable to reversal. And I want to emphasize some of the ways that we think that storing carbon through engineered carbon removal technologies can permanently remove CO2 from the atmosphere. I think that's the real differentiation between land-based and biological approaches and engineered approaches to carbon dioxide removal. Has to do with the durability or the permanence of the approach, and whether or not we can trust that carbon has been removed from the atmosphere is going to stay removed from the atmosphere for several centuries or millennia, consistent with the scale and the time frame of climate change and the climate challenge. So I want to start by talking about direct air capture of CO2 from the atmosphere, in part because it's probably the easiest engineered carbon removal technology to think about. What happens here is that ambient air, which contains 400 parts per million of carbon dioxide, is passed over some kind of solvent or sorbent, which attracts CO2 and pulls that CO2 from the air. The CO2-free air is then is then removed from the system, and heat and electricity are required in order to regenerate the solvents and sorbents that have absorbed the CO2. That produces a concentrated stream of CO2 that is available for geologic sequestration. In the case here, this is the first commercial direct air capture plant in the world. It is in Iceland, and it's using a technology pioneered by a company called Climeworks. They're actually injecting the CO2 into a basalt formation where it rapidly mineralizes and turns into carbonate materials. This means that the CO2 is locked up almost immediately, thus providing a very long-term and very secure form of carbon dioxide removal. Direct air capture is a technology that's in early stages, but I think there are a lot of exciting opportunities. They can be placed in a range of different places. They can be relatively modular, and they can be integrated with storage in order to permanently remove CO2 from the air. And we're seeing really 2 or 3 companies stand up and start to commercialize this technology. One relies on a very large scale, very centralized process. That's a company known as Carbon Engineering, which operates in British Columbia. They're planning on building facilities that pull between 500,000 and a million tons of CO2 out of the atmosphere per year from a single facility. In contrast, Climeworks, who has built the first commercial plant, is taking a much more modular approach. They want to build smaller units that don't look much larger than air conditioners, and they want to really pursue kind of modular and small scale market opportunities where there is demand for carbon dioxide removal or from pure CO2 by these machines. And this is a technology that I think is deployed in niche markets. It's not quite ready to scale, in part because of its relatively high cost. I think most reputable estimates of direct air capture using present technologies, at your most optimistic cases, you're going to be looking at about $200 per ton of CO2 removed from the atmosphere and permanently stored. And I think current technology is likely on the order of $500 to $600 a ton. So there's substantial innovation, substantial technological learning, and substantial cost savings that need to be realized before this technology can really compete with managing ecosystems or managing forests and storing carbon using much lower technology approaches. A second emerging engineered carbon removal technique is known as enhanced weathering. And this is actually a relatively early stage technology. It has not been deployed at any appreciable scales yet. But what it does is it essentially involves mining and exposing carbonate materials and silicates. Think of rocks that are available all across the world. Involves mining them and exposing them to CO2, where you can where you can speed up the rate of weathering, also known as CO2 fixing, where you're forming carbonates. This allows you to pull CO2 again directly out of the air and store it stably in long-lived mineral carbonates. We expect that they are stable on the time scale of tens of thousands to hundreds of thousands of years. Unfortunately, there's a lot we don't know about these systems. We don't know how to design or engineer them. We're lacking some basic knowledge around which materials are best suited for enhanced weathering. There's also a lot of uncertainty about the impacts on mining, the energy requirements, and related kind of pollution impacts with implementing this technology. I think it is a very large scale technology, but it's one that's relatively early on. And the third carbon removal technology, and the one that I want to spend the most time focusing on today, in part because I think it's nearest to commercial deployment, is bioenergy with carbon capture and sequestration. The third of the three techniques that I had mentioned before. The basic idea here is that rather than pulling CO2 directly from the air, we are pulling CO2 from biomass. Biomass, of course, grows using photosynthesis. It fixes CO2 from the atmosphere. That biomass is then harvested and transported to an energy conversion process coupled with carbon capture technology. And what it allows you to do is to create two products. One is an energy product. And the other one is CO2 that's available for compression and geologic sequestration. Again, this CO2 is meant to be compressed and put underground in deep geologic formations, where we expect it to stay for centuries or millennia. Bioenergy with carbon capture and sequestration, or BECCS, as it is colloquially known, it can take a lot of different flavors. And I want to walk you through some of the ways this can work and some of the subsystems involved. As I mentioned before, it typically starts with harvesting biomass. These can be wastes and residues that are the byproducts of agriculture and forestry operations. It can be our trash. Or it can be purpose-grown energy crops, much like the focus of a lot of research at Iowa State University. Again, there are a range of capture and conversion processes that we use to turn biomass into different energy products. Some of them use biology, like fermentation or anaerobic digestion, in order to create gaseous or liquid fuels. And some of them use chemistry, gasification, pyrolysis, and other catalytic conversion of the molecules contained in biomass allows us to produce a range of energy products. These can be liquid fuels like ethanol or drop-in gasoline or diesel. These can be gaseous fuels like hydrogen or renewable natural gas, or it could be electricity or heat. At the same time, again, the CO2 that is a byproduct of this energy conversion process is captured, compressed, transported, and stored underground in deep geologic formations. And Phil, I think, gave some really excellent context for why and how we need to scale negative emissions technologies. And this is a very large scale problem. if we look at the kind of best available science, the most representative pathways by which we're going to be able to keep or to meet the goals of the Paris Agreement to keep global warming at or below 2 degrees Celsius, warming above pre-industrial temperatures by the end of the century, we're going to likely need billions of tons of carbon dioxide removal, not just in the second half of the century or not just by 2100, but starting as early as 2025, really deploying this at a scale, an unprecedented scale, a scale not of millions of tons or thousands of tons of CO2, but of billions of tons of CO2. And in fact, the median model outcome for 2 degrees Celsius compliance scenarios involve typically on the order of 10 billion tons or more of atmospheric CO2 removal per year by the end of the century. So this is going to be a large-scale industry if it's going to make a difference in the climate fight. Unfortunately, rather than the 10 billion tons of CO2 per year that we have right now, the current deployment of bioenergy with carbon capture is about 1 million tons of CO2 per year. This is a plant, a wet mill ethanol plant owned by Archer-Daniels Midland in Decatur, Illinois. They are capturing and compressing a million tons of CO2 per year and storing it underground in the suitable geology just nearby. It is about 1/100th of 1% of the median 2100 deployment that we might envision needing for these scenarios and needing for scale for engineered carbon dioxide removal. But nevertheless, it's a start, and it's storing again in the suitable geology. In this case, it's known as the Mount Simon sandstone that underlies much of Illinois, Indiana, and Kentucky. What's happening here is they are taking a source of CO2 that comes directly off of fermentation. The biological conversion of sugars and biomass in order to make ethanol gives off a byproduct of CO2 that is relatively pure. And all that's necessary in order to do this is to run this through a series of pumps and compressors to compress that CO2 up to what's known as a supercritical fluid, where it's indistinguishable between a gas and a liquid. It is then pumped underground about 6,000 feet into the Mount Simon sandstone. There are 3 geologic seals on top of where this CO2 is being stored, and so we're quite confident that the CO2 is going to stay in place, and then it's going to be able to semi-permanently remain out of the atmosphere. We're interested in a lot of different approaches to bioenergy with carbon capture, including ethanol biorefineries, as I just mentioned, a range of other fuel production processes, things like biogas production, things like creating other biofuels through gasification or through pyrolysis. But we're also interested in expanding the scope and thinking about not just capturing and storing geologic CO2, but thinking of long-lived wood products and other long-lived biomass products that store CO2 out of the atmosphere and can help contribute to again, keeping that CO2 out of the air and carbon dioxide removal. This can be a range of bioproducts, things like bio-derived polyethylene. This could be engineered wood products like mass timber or cross-laminated timber and other kinds of long-lived wood products that we put into buildings. And there's a range of other approaches. We've even looked at the idea of running direct air capture machines on bioenergy to synergistically move or pull more CO2 out of the atmosphere. I want to focus on an opportunity that's emerging right in Iowa today around ethanol biorefineries, because this is the nearest term action that I see on engineered carbon dioxide removal. So I want to walk you briefly through the idea of capturing CO2 and sequestering it from the existing biorefineries in the United States. And just to keep with time, I'll move through these slides relatively quickly. It turns out that because the CO2 that comes off of fermentation is relatively pure CO2, it's just CO2 and water, there's no need for the costly carbon capture steps that plague a lot of other carbon capture and sequestration technologies. In fact, we think that we can compress CO2 coming off of ethanol fermentation and put it in a pipeline ready for sequestration at a price of under $30 per ton of CO2. This is at least half the price of any other CO2 capture system that's going to work with less concentrated sources of CO2. We also, of course, have about 200 existing biorefineries in the United States, many of which already capture their CO2 and sell them into existing merchant markets, whether that's beverage carbonation, dry ice, or chemicals. And then, of course, we're doing this at one facility right now in Decatur, Illinois, at the Archer Daniels Midland plant, where they're capturing and sequestering 1 million tons of CO2 per year. Again, we have about 200, just over 200 biorefineries across the United States. Those are shown in the dots with both the color and the size indicating their scale. Those are concentrated in the upper Midwest, in Minnesota, in Iowa, in Nebraska. These are places where, of course, we have a large bioeconomy, but not necessarily suitable geology in order to store CO2 underground. Which is, of course, is necessary to make sure that that we're achieving carbon dioxide removal. And so we're really interested in understanding what it's going to take to capture the CO2 from these biorefineries, move them to where they can be suitably stored underground, and then understanding the costs, the emissions implications, and the overall feasibility of this. We're using a number of engineering methods, including process engineering, geospatial optimization, and life cycle assessment. And I'll take you briefly through these results. First is we find that we can measurably reduce the carbon intensity of fuels produced from corn ethanol by just capturing the CO2 associated with fermentation. We're looking at approximately a 40% carbon intensity reduction. You can get even lower, of course, and there's actually even the prospect of making corn ethanol a zero carbon fuel by integrating more and more renewable energy, as well as carbon capture into these processes. And we try to simulate what it would take to build CO2 capture and sequestration networks, ultimately designed to put CO2 underground at different prices. At a price of $30 a ton, we see a relatively small industry, about 10 biorefineries capturing 6 million tons of CO2. That white dot, or that black dot in the center of Illinois right there, is conveniently the Decatur site, where they're actually already doing this and putting CO2 underground. At a price of $60 a ton, however, we see a lot more opportunity. We see an opportunity to build large-scale integrated pipeline networks to capture CO2 from about half of the biorefineries around the United States, and sequester about 30 million tons of CO2 per year. This is out of the 45 million tons of CO2 per year that come off of ethanol fermentation. It also allows us to double the amount of CO2 pipeline in the United States, going to about 4,000 miles of CO2 pipeline. Again, capturing CO2 from these biorefineries and moving them to where we can put the CO2 underground. This is a zoom in on the Midwest. And we see similar results, of course, at $90 a ton and higher prices, more and more CO2 being captured and more being put underground. The vast majority of this CO2 is available for under $50 a ton. And I'm excited about that because we have supportive policy in place in order to push that forward. I want to walk through two different policy drivers and policy impacts associated with this opportunity to capture CO2 from biorefineries and put it underground. The first is a CO2 sequestration tax credit that was actually passed by the US Congress, available to biorefiners across the United States in the year 2018 and finalized actually just in the year 2020 after several regulations were put out. That will pay you up to $50 per ton of CO2 to put CO2 underground for a 12-year duration. Now that's getting very close to the break-even economics of capturing CO2 from biorefineries, putting it into a pipeline and moving it to where it can be geologically sequestered. But on top of that, we're actually seeing the emergence of low carbon fuels policies, including, for example, California has a low carbon fuel standard, which will pay up to about $200 per ton for CO2 abatement associated with creating low carbon fuels. California went through the process of actually putting a methodology in place for carbon capture and sequestration at biorefineries and refineries, with an idea that they would be able to install carbon capture and sequestration and use CCS as part of creating low carbon fuels. Now, if you put these two together, that's a price of about $250 a ton for carbon capture and sequestration, which is vastly in excess of what we estimate the cost to be. I'll also note that we're seeing a proliferation of low carbon fuel standards, including many discussions in the Midwest I think low carbon fuel standards are going to be a real driver, not only of lower carbon biofuels, but also of biofuels coupled with carbon capture and sequestration moving forward. Again, the price has remained relatively stable for the past several years in the LCFS credit market. It's essentially floating at its price ceiling of about $200 per ton. I just want to conclude by saying that, within engineered carbon removal technologies, I think there's this real opportunity to start with our existing infrastructure and our existing biorefineries to achieve this vision of bioenergy with carbon capture and sequestration. It's likely going to involve the construction of integrated pipeline networks, but it will allow us to get and reliably and profitably remove tens of millions of tons of CO2 per year from methanol fermentation. And this has an opportunity to grow carbon capture infrastructure, to improve the life cycle impacts of conventional biofuels, and help fulfill the mandates of low carbon fuel policies across the US. I just want to finish with one last thing. 2 weeks ago, there was actually an announcement of a very large integrated CO2 pipeline financed by a company called Summit Carbon Solutions that's planning to connect 20 different biorefineries in northwestern Iowa, South Dakota, and southern Minnesota. They will be connected together, and the CO2 will be moved in a common carrier CO2 pipeline to North Dakota, where it will be stored underground. They're planning on building a pipeline that can move about 10 million tons of CO2 per year. And the 20 biorefineries they've already contracting with are expected to reduce their carbon intensities by about 50% each. This is an example of the kind of scale, the kind of aggregation, and the kind of work we're going to need in order to continue decarbonizing our transportation fuels and ultimately scaling up engineered carbon dioxide removal at scale. I'll stop there because I'm over time, but I look forward to any clarifying questions, the panelist discussion, and the Q&A. Thank you so much.
And thank you very much, Dan, for that informative discussion. In fact, it's generated a bunch of questions that I want to be careful of our time. Ali, should we move these questions to the discussion time, or do I have time to raise some of these with Dan now?
Let's start raising some of the clarifying questions. Ryan, would you mind kind of helping cipher through the more clarifying ones, and we'll go from there?
And I'll start because I've been looking at some of these. The first is from Mike Long, is asking about the Chevron Gorgon CO2 injection process. I think what's needed here, Dan, is a clarification between fossil carbon capture and sequestration and true carbon removal. Could you help us with that?
Without a doubt. So carbon capture and sequestration is a technology that can be applied to a lot of different things. We had originally thought it would be really useful for coal-fired power plants, and that was the source of a lot of research and development over the past 20 years. It turns out that carbon capture can also be used to decarbonize existing industrial processes like steel and cement production. It can be applied to biofuel production processes. It can be applied, to directly pulling CO2 from the air. The primary difference has to do with when you're applying CO2 to fossil fuels, what you're doing is you're digging carbon out of the ground, oxidizing it, capturing that CO2, and putting some of it back down. So at best, you're at carbon neutrality for the energy that you can produce from fossil fuels. When you're dealing with biomass and when you're dealing with carbon dioxide removal technologies, you're actually taking that CO2 directly from the air or mediating it through biomass that has recently grown. And so the whole process on a life cycle basis actually allows you to remove CO2 from the atmosphere. And so your fuel's emissions footprint or your carbon intensity, it won't be above zero like fossil fuels. It won't be at zero like zero carbon fuels, for example, if we made them from wind and solar, but they will actually be carbon negative. So the production of energy removes CO2 from the atmosphere.
Thank you. And we've had an interesting discussion that started with Ellen Moss asking about, if you're going to put this CO2 in a saline aquifer, aren't you going to start producing carbonic acid? And it's looked like, I'm sorry, I've lost the person. Betsy Swanners responded that, well, it's going to actually be generating bicarbonate ions, which is going to be an effective way to store the CO2. Could you clarify?
Absolutely. So when we put the CO2 underground in deep geologic formations, I think many people are targeting saline aquifers because they're well known. They typically don't have other uses. They typically have a lot of empty pore space or pore space that's filled with brackish or very saline water. Once we inject the CO2 down, there's actually a variety of mechanisms that increase in security over time to help us be sure that the CO2 is likely going to stay there. The first thing that happens is it just dissolves. You're right; it creates the bicarbonate ions. The second thing that happens is it actually is trapped in capillaries and little small parts of the pore structure of the geology. And then finally, over time, it actually does mineralize. Just like we had talked about with enhanced weathering of carbonate materials, it will form a carbonate, and it will form a very, very secure form of geologic storage. So it's multiple mechanisms kind of all interacting with each other that make us so sure that the CO2 will stay underground.
Very good. And Bruce Dale asked about, since the need to capture carbon is immediate and most engineering approaches are mostly expensive and energy intensive, does this mean we need to be starting with land-based approaches, or would you argue otherwise?
I've always been an advocate for a full portfolio of solutions. I think all of these technologies are promising and all of them can be likely scaled up. I would advocate for near-term action on biological carbon removal, particularly in the United States, while also using our scientific and engineering prowess to start piloting, demonstrating, and driving down the cost of these engineered carbon removal technologies. I think that portfolio approach gives us the best chance of success. It also helps us to learn what's going to work and what's not going to work over time. I can spend a lot of time being really skeptical about biological carbon removal, but the fact of the matter is we can do it right now. It will provide carbon benefits for short periods of time. And it also involves it involves industries like production agriculture. It involves landowners in a really politically exciting and motivating way. I think the politics of carbon removal are such that we should afford to have kind of a big tent and really include all the solutions, at least at this early stage.
And one final one, Ellen Audius asked, well, how much geological area is going to require to do this storage? Can I restate that? What is our capacity to remove all of our CO2 emissions in geological storage?
The good news is that at least in the United States, we're talking about hundreds to thousands of years of geology that can suitably store CO2. So if you compare the amount of CO2 that we put into the atmosphere compared to the estimated storage potential, it's several of orders of magnitude different. And so we don't foresee large-scale constraints on geologic CO2 sequestration capacity. The primary problem is that you really do need to move the CO2 to where you have the suitable geology. And unfortunately, through an accident of evolution, that is not in the upper Midwest. You're going to have to move the CO2 to Illinois, you're going to have to move the CO2 to Western Nebraska, or you're going to have to move the CO2 to North Dakota. And that's going to be the real primary constraint, I think, rather than any injectivity or any overall storage constraints.
Thank you, Dan. And let's give Dan a round of virtual or real applause. I'll give some real applause here. Okay. We're ready for our panelists, if I'm not mistaken. And these include Professors Mark Mumba-Wright, Dan Anderson, David Laird, Yu Wong, and student Elaine Leonard. So we'll get them on here. They will each make a short response, and then we'll go to the discussion with the group. And we'll try to catch some of these questions that appeared after. Boy, a lot more have appeared. Good luck, Ryan, sorting through all of these. Okay. Shall we start with Mark?
Thank you, Robert, and thank you, Dan, for so eloquent and clear presentation. I really was inspired by how you presented all these scenarios and technologies addressing the climate challenge that we're facing today. In particular, I liked your dimension across the agriculture and engineered solutions. And I envision that there's another axis here about social political acceptance. of these technologies. And in my view, BECCS still remains at the center of that intersection because, as you mentioned, we have scale-up challenges, economic cost challenges. And if you look at engineered solutions versus agriculture, I believe that agriculture has demonstrated large-scale flows of carbon across the atmosphere. It's no secret that agriculture has been a major player in human development. And compared to the industrial flows of emissions, even though they've had a big impact, they're still orders of magnitude smaller than the carbons that are moved by our agricultural systems. So I think that's something that BECCS can certainly leverage. And this is important because if we're going to leverage agriculture, we need to have an incentive for farmers, an incentive for public agencies to support it. And I think in the near term, that's something that plays a major role. And we're seeing that with the ethanol industry in your presentation. But we also need to think about solutions that develop, that can be scaled up from small scale farms, even in developing countries. I know that a lot of your presentation was US based, but if we're going to meet the global challenge, we need to move technologies that go all across from those small scale farms in developing countries to fully industrialized operations. So based on what I saw today, I'm really hopeful. I think that the way you described and clarified some of the terms and challenges that we're facing will hopefully also inspire other participants in the forum and elsewhere. Thank you.
Thank you, Mark. David, we're going to turn to you next.
Well, thank you, Robert, and thank you, Dan. Really appreciate the presentations today. I'm a soil scientist by background, so that's my perspective. And the other key point I'd like to make is how can we capture additional value? The concept of geological sequestration of CO2 is inherently a waste disposal process that adds no net economic value. I certainly support a full portfolio, but if there are synergistic ways of capturing additional value through carbon sequestration, those are going to be the low-hanging fruit, at least in my judgment. And two of the areas that you mentioned today, I believe, have some possibility for doing that. And the first is the enhanced mineral weathering. Speaking as a soil scientist, there are vast areas of primarily tropic and subtropical regions of the world in which we have highly weathered, degraded soils. The application of basalt or mafic mineral particles on those soils would actually improve the quality, add nutrients, and enhance productivity on those soils. So if there's a way we can combine soil regeneration with enhanced weathering, I can see the potential for synergistic value. And the second area, of course, is BECCS. And my particular piece of that has always been the biochar side of the equation. And certainly from cellulosic ethanol, thermochemical production of bioenergy products, if there is a biochar co-product, as opposed to a simply the direct injection or geological injection of CO2. Again, I think we have an opportunity to capture additional value. And so with that, I'll just draw it to a conclusion. But again, thank you for the presentation.
Thank you, David. Yuke, would you like to speak next?
Oh, yeah, sure. Thank you, Robert. And thank you, Dan, for the excellent presentation. I feel motivated after your presentation because you have suggested great potential, especially with cellulosic ethanol. That's something I think that's more like wow to me, at least, because you were able to connect all the great potential in technology with all the policy drivers and potential economics. So that's wonderful. So my background is energy policy analysis. So I want to speak a little bit more on that side. I have also been doing research analyzing renewable fuel standard and LCFS and how that will impact cellulosic ethanol in the future. So according to my analysis, I found that the current policies are still lacking significant motivation or incentive to make sure the industry to develop in a fast way. And we can also observe that when we take a look at the biorefineries in the Midwest. You have shown us a map that having over 200 biorefineries in the US, but I think only a few of them are cellulosic ethanol plants. And if we look at the ethanol plants in Iowa, more specifically, one of them has been shuttered for some economic reasons, probably. The other one that's close to Ames here was converted to produce renewable natural gas. And I believe that's motivated by California's LCFS, because they found out that they can sell their renewable natural gas at a much higher price. And it's a better business model than cellulosic ethanol. So it's actually very interesting for me to see that you believe LCFS can be a big policy driver for cellulosic ethanol. But currently, it seems the current market is providing a much stronger incentive for renewable natural gas. So I really love to see maybe you can discuss that in a little bit more details. So yeah, excuse me, this is more like a question, not a comment. Thank you.
Thank you. I'm going to turn this over to Elaine now. Elaine is a student actually studying carbon removal. So we're real interested in her response to your remarks, Dan.
Hi, my name is Elaine Leonard. I'm currently a chemical engineering student here at Iowa State. I'm studying under Dr. Brown. My major focus is running economic analyses for some of the new emerging technologies for carbon removal. So basically to find feasibility for implementing and scaling these operations. It's really nice to know that there are certain specific companies that are trying to do their best and working towards more carbon negative and carbon neutral just policies and motivations for them. So, yeah.
Thank you, Elaine. And finally, our other Dan, but I think we'll call him Daniel Anderson, who goes by the way Dr. Manure, in case you want another name for him. So Dan, take it away.
All right, thanks, Robert. And thank you for that great presentation. There was a couple things that really caught my interest. The first, I always appreciate seeing the mechanical carbon capture from the atmosphere. As an ag engineer, it makes me feel like, can we design a better plant, right? Not a big industrial plant, but an actual physical green growing plant. And the mass transfer to get all that carbon to one location and captured is interesting when and I appreciate you pointing out biomass. And in many ways, biomass already handles that problem for us, and it turns it into a transportation problem to turn it into a fuel and capture it. And I think you did a really wonderful job talking to that and pointing to some of the opportunities and challenges we have, especially related to the low carbon fuel standard and the potential that has to incentivize carbon capture both at the plant. I like anaerobic digestion, so capture of CO2 from anaerobic digestion and maybe storage or maybe potential to turn it into, as Dr. Laird mentioned, a more valuable product. And looking at the production chain there, the opportunity to pass some of that savings back to farmers, right? I mean, you pointed out the Summit project where there's a great opportunity for CO2 storage in reservoirs, and I'm really excited to see that. But thinking about how to incentivize that back to farmers who are growing the biomass and storing that carbon for us, I think has a lot of potential, and the low carbon fuel standard sort of sets off some of that trading possibility.
Thank you, Dan. That's useful. We're going to now turn to the discussion questions. Ryan Smith is going to help me by trying to make some order of all the questions that are coming in. Let's keep in mind that when we talk about the engineering side, sometimes this kind of drifts into the area of geoengineering, which has a bad name in some areas. And So I think that also brings up some concerns about, is this the arrogance of engineers? I can say that because I'm an engineer. So, okay, Ryan, can you help us?
Yeah, sure, Robert. There's a few questions that address this. So I'll try to do this in kind of one question and address all of them. But the first was, it was kicked off by Dara and then plus one and added to in different ways by a few people. And that is, how do you address the potential for public concern of new pipelines and injection sites? And related to that, how does the transition to EVs change the urgency or the perceived urgency to implement some of these solutions?
Sure, I can start to start that discussion. Would welcome input from anyone else. You know, I think there is concern that new pipeline construction is not going to be politically feasible in the United States. You know, I would imagine that looks a little different in the Midwest than it does, say, where I am in California. But you know, we're considering doing the same thing actually with carbon capture and sequestration networks, primarily with the Central Valley of California, where we have a lot of an industry, a lot of agriculture, a lot of cement production, for example, and also really good geology for storage. We found that public knowledge of this is relatively low, and that people are at least willing to listen to a story about how this is a very different kind of pipeline, one that is contributing to climate restoration rather than climate destruction. That being said, it's early time, and we have seen some significant backlash to CO2 sequestration projects. I'm hoping that is something that can be overcome. Gosh, and there was a second question and I totally forgot it now. Sorry, Ryan.
Yeah, Dan, it was just the question of follow-up to that is, with the transition to EVs, how does that change the ability to sell that case, or the urgency or perceived urgency by the public?
Sure. So we're actually, again, looking at a very similar question in California, where the governor has said that the state is not going to sell internal combustion engines after the year 2035. They want everything to be either an electric vehicle or a fuel cell vehicle for light duty vehicles. And we have goals in 2045 actually to apply that to medium and heavy duty vehicles as well. I think this brings up I think it disadvantages some of the near-term opportunities to create liquid fuels out of biomass, but I actually think it really greatly advantages some of the other approaches. One thing we're particularly excited about is actually carbon negative hydrogen production in the state in California, typically our waste agricultural and our waste forest resources. Biomass contains carbon, hydrogen, and oxygen, and that carbon was recently fixed from the atmosphere. If you want to make hydrogen, that means you can capture all of that CO2 and store it underground. It's about the most energy dense fuel you can make. It's also about the most carbon negative fuel you can make. And so it kind of hits that real sweet spot for, okay, maybe this can be used in, new and advanced vehicles. This can be used kind of in and throughout industry, including in the production of like oil refining and steel and cement production. Again, it's kind of this trade-off between the carbon value, the energy value, and scenario planning. And it's rapidly evolving.
Thank you.
Okay, another question, Dan. Mike Long asks, with the concerns about pipelines, how feasible is it to transport CO2 by rail or truck?
It is absolutely feasible. And we've actually proposed near-term implementation in California, moving by way of truck. Particularly when you're dealing with small volumes or relatively short distances, the economics can be better than moving CO2 by pipeline. So that's exciting. That's done in a couple of places. Actually, it's done with a couple of biorefineries already that are using their CO2 for enhanced oil recovery. Again, it's a way to get around the pipeline issue. I see Emily just chimed in that ADM is also moving their CO2 by truck, which I was not aware of. So it absolutely is something that we can do. If we move to a large scale, CO2 transmission network, CO2 transportation network, and, if this really turns into an industry, I think there are a lot of economies of scale to be realized from going to pipelines. Whereas I don't see similar kind of economies of scale in truck and rail transport.
Okay. And Charles Sukup had a follow-up question for you, Dan, on one of your recent comments. What are examples of backlash to carbon sequestration that you're referring to?
Sure. So, in this case, there are two examples. One is a fairly old example in Europe where geologic sequestration on continental Europe. It's something called Schwarze Pump. It was a project in Germany. And I think the project was fairly poorly communicated, and it was really early times for CCS, but actually public backlash led to the cancellation of the project. And we've seen similar examples in the UK as well. Another example would be a lot of CCS projects that are tied up in more fossil infrastructure. There was a proposed petcoke gasification plant that was going to make hydrogen and capture the CO2 and put it underground in Kern County in California, which is the kind of the center of the oil and gas industry. And I think it was really environmental justice interests and anti-fossil fuel campaigners in the state of California that led to that project being canceled. So, not a particular knock on the CCS, but what the CCS was being applied to, which is exploitation of a fairly dirty fossil fuel to make more fossil fuels.
And Ryan, I'm going to jump in here. I see a question by John Creasby of the Card Center here at Iowa State University that does a lot of economic analysis. And Dan, I'm just going to read a quote directly. For real estate projects, California is not a, quote, shovel-ready state. It is a, quote, litigation-ready state. I do think this is a big issue, but the Midwest might be more open to it. Would you care to comment?
I think that's absolutely the case. I think we need to find people who are going to be champions of this. There are ways that this makes sense in California from a resource perspective. We have a tremendous amount of waste biomass resources that we are open pile burning, particularly agricultural resources in the Central Valley, or forest residues, the byproducts of forest operations that essentially are sitting there in the forest, waiting for the next wildfire. So I think there's a big need in the state of California. But where I think this is going to happen first is through places where there is an existing bioeconomy and a thriving bioeconomy. That's going to be both the Midwest and the Southeast. Particularly, I think very, very low timber prices in the Southeast could lead to the first kind of commercial scale cellulosic ethanol or lignocellulosic fuel production facilities that are really kind of coupled and captured with carbon capture and sequestration. The Southeast also has good geology for storage and compared to the Midwest. So I would say, you want to look to the places where you can do this, and it's about getting a couple of projects on the ground so that more people can become aware of it, and we can evaluate where there's going to be social acceptance and where there's not going to be social acceptance.
I'm curious whether any of the panelists would like to comment on the relative competitiveness of the Midwest compared to other parts of the country. Anyone?
Well, I will say that certainly we have the beginning of the bioeconomy here and set in grain ethanol, but that is obviously first generation stuff. But at least there is, I think, broad political acceptance for that here. Other parts of the country, however, there are opportunities for synergism. You mentioned the wildfire challenge out in the West. Any systems in which we can remove some of that fuel, whether it's slash or whether it's dead bark beetle killed trees from the forest, and turn that into some kind of either bioenergy or carbon sequestration. Again, you're adding value by mitigating the forest fire risk. So those kinds of activities could leverage political support, I would hypothesize at least.
Mark?
And I would like to add, I know most of the discussion has centered around gaseous CO2 going through pipelines, but if you extend the discussion to solid forms of CO2 like biochar, then I think the Midwest has other important incentives in terms of how we rejuvenate the carbon in our soils, how we utilize some of the biomass that we need to improve conservation and ecological services in the area. And when you take that put together, then I think public support will be fairly strong.
And adding to that, I mean, if we're going to harvest biomass, the Midwest has a vast experience with animal agriculture. Many times where biomass is harvested as a bedding material, we have people who know how to collect it, know how to move it around, and that is a value to the industry. We do have a viable livestock population. It's a large livestock population in Iowa, where we bring a lot of product that's often looked at as a waste to one source, and we're relatively good at economically redistributing that, all things that will be important if you're dealing with large amounts of biomass. So I think we do have some advantages. And if you start looking at the capacity of Iowa and the current RIN market, I think if we anaerobically digested all the manure in the Iowa, mix that with 70% of the corn stover we could harvest on those livestock farms, we'd maybe get close to filling up the amount of RIN cellulosic ethanol that's currently available, right? And that's an arbitrary number set, but we can actually make feasible differences in the amount of renewable energy we're creating.
There's been a lot of discussion about, well, why are we even talking about chemical energy? We're going to electrify everything. I've seen that theme kind of appear. So this is a specific question that comes from Rocky Quarry. Transition to EV transportation will simply put more stress on electric generation and transmission systems to move out of natural gas generation as well as coal. I mean, that's going to put additional stress. So I guess the question is, with your expertise in electrical power systems, are we going to run into trouble in going to this electrification approach?
Was that question for you in particular?
For you, I'm sorry, you won't.
Yeah, thanks, Robert. I do have a little bit background in studying the electric power sector. So I actually don't think that's additional pressure. Currently, the biggest challenge to the current power grid is the integration of renewable energy. We are transitioning to a more cleaner system here. So adding EV to this actually provide additional potential to balance the system, because you can actually manipulate when you will charge your EV, and that will provide additional potential for providing flexibility service to the grid. And that's what is currently needed, because we need flexibility to balance and support renewable energy, such as wind and solar. So I personally, I do not view EV as an additional challenge to the grid. But again, there are a lot of technical challenges here when we try to have a more integrated vehicle to grid system. There are a lot of challenges on that side.
David.
Certainly, I see the movement towards EV and building out the grid is critical. But I want to also emphasize that there is a limit to electrification. Certain sectors of our economy, jet transportation, marine transportation, and agricultural vehicles, combines, earth-moving equipment, all will require high energy density liquid fuels for the foreseeable future. And as long as those are produced from fossil fuels, we're going to have to more than offset them if we can produce them from biomass or from direct air capture of CO2 and electrochemical reduction of that CO2 to hydrocarbons. Then we have made a further step down the roads towards decarbonization. But we're not going to get away from liquid fuels for the foreseeable future, at least in those strategic areas.
And I don't see this question, but I want to put, as my student, I want to put Elaine on the spot. As a student, what do you see the opportunity for students, or what do they need to be doing to be prepared to do some of the things that Dan has outlined as possibilities, or that we heard earlier on the agricultural side?
I think just talking as sustainability in general, I think it depends, like as the younger generation kind of gets into the workforce, just implementing sustainability or working for sustainable companies with good green initiatives, I think is important. I also wanted to address the question about like discussing with peers. Right now, I'm currently in a club on campus called Engineers for a Sustainable World. So with that, we have smaller subgroups that are working on different projects. So they're really into, there's one that's into solar, one that's it's basically just like small implications on campus that we can do as students. So composting, solar panels, that kind of thing. Personally, I am really into offshore wind energy and to see how that comes to fruition. And I think also nuclear, although it's not technically renewable energy, that also has a lot of potential just because of the efficiency that it has. So.
Well, as you can see from Elaine's answer, our students are not Iowa-centric, willing to look at offshore wind generation. Before we move from the topic of education, was anybody, Dan or the panelists, have any comments about what they think is going to be required in education as we currently teach our students?
I would say that engineering fundamentals are absolutely key to being able to talk about energy and climate change challenges. I myself was a chemical engineer as an undergrad, just like Elaine was, and learned a lot of just really basic numerical literacy. I think on top of that, though, understanding emerging technologies is inherently an interdisciplinary question. I spent most of my graduate training looking into public policy, into economics, into techno-economic assessment. And I think it's really, it takes an understanding of kind of more than just one discipline to work on technologies that just don't exist yet.
Others comment? Educational focus? Mark?
Yes, if I could add. So actually, this is kind of promoting a new article that will be coming out on biofuels, bioproducts, and biorefining. I know Virsdale is in our audience. A group of graduate students and undergraduates that were part of a bioeconomy leadership program are writing a review paper on how students are exposed to the bioeconomy and what are some of the changes that we can make in education to help them become more aware about what's needed to move the bioeconomy forward. And so I'm looking forward to hearing what the students will have to say in that article, and I hope that you'll have a read as well.
Very good. And I see Lisa's face has appeared on the screen. So I think that's equivalent to pulling me off the stage, if I'm not mistaken. So I want to thank first Dan for his presentation. You've generated a lot of interest among our faculty and other participants, as well as our panelists today. So thank you. If we can give them a applause.
Thank you.
Lisa, it's your show.
Well, thank you, Robert. Thank you, Dan, and all the panelists, and the great questions from our audience members. Wow, this is just so fantastic. I'm so excited by this discussion. And we're going to hear now a little bit more about what ISU is doing in this space. And now from Dean Dan Robeson. He's the endowed dean for the College of Agriculture and Life Sciences here. So Dean Dan.
Great, thank you, Lisa. What a terrific morning. I'm just so impressed by all the conversation. Lisa Schulte-Moore, Robert Brown, thank you so much for bringing this to us. It's really an incredible group of people who have tuned in for this today or zoomed in for this today. And I just want to congratulate everybody on this terrific conversation. I know I have just a few minutes. I'm inspired to talk for an hour though, but I won't. We're late in the morning here. But let me conclude in a couple of ways. First off, of course, context is everything, and we're talking about a topic which is not only at the smallest scale, but is admittedly at the very, very largest scale. It's a planetary scale kind of issue we're facing. And so during the conversation today, I reminded myself of some of the bigger picture items that I think are important for us to keep in context. So when I was born in 1960, there were 3 billion people on the planet. Today, with basically the same land area, there's 7.2 billion. And in just a few decades, it'll be somewhere around 10 billion. That is an incredible challenge for us to deal with in terms of providing food, providing living space, transportation, and no less energy and carbon management. And let us not forget water too. That's one thing to keep in mind. Another thing to keep in mind is that today on the planet, 7.2 billion people, and it's gotten worse, 7.3. It's gotten worse over the past year with the pandemic. A lot of our brothers and sisters live in poverty. Extreme poverty, less than $2 a day, is about 10% of the world population. But I think we'd all admit that $2 a day is a pretty low bar. Let's set the bar a little bit higher at $5 a day. And of course, you and I, if we're on this call, we use more than $5 a day before we wake up in the morning. Nearly 50% of the world population lives on less than $5 a day. So when we think about scale and economy, we have an enormous challenge, not just with respect to landscapes and soil carbon, but all the people that are depending on those landscapes in order to be able to thrive and survive and not exist at the level of subsistence they're at now, but to have a higher standard of living, frankly. Again, some of us, probably most of us on this call, could afford to reduce our standard of living even by a little bit, but most of the world's population needs to vastly increase their consumption of resources. More books, more education, more healthcare, more energy, more of everything. And so the challenge is incredible and formidable. There are terrific examples, though, of how this can be done, and we can do this. I spent a lot of my career in the further east in the US, and I'll remind you that in the 26 states east of the Mississippi, there's about 1 million square miles of land. When Europeans first arrived here, probably 90% of that was covered in trees. By the year 1900, only 25% of that was covered in trees, and the other 75% was highly, highly degraded. Today, through recovery of those forest systems, nearly 65% of that 1 million square miles east of the Mississippi is covered in trees, and arguably has sequestered and is holding far more carbon than it did 120 years ago or so. We have a similar challenge here on what used to be prairie and now is mostly in cropland. Not that we're going to give up our cropland, we have to produce food, but nevertheless, how do we, and I'm going to coin a new word here perhaps, and that is to repair our landscapes. So we've talked about reduction and removal, but let's think about repair as well. What we're sitting on is a massive amount of deferred maintenance of our soil enterprise, and we've got to do some repair work, put carbon back into it, put organic matter back into it for all the reasons that are out there, both fertility as well as carbon management. So lots of challenges, but lots of opportunity to affect how we manage broad swaths of landscape. Seems to me that probably the most effective policy to date on landscape management, besides the fact that lots of land was worn out through previous agricultural practices and went back to native vegetation, but the most proactive policy has been the Conservation Reserve Program. We're in its 40 years of existence, something like 30 million acres have gone back to more perennial vegetation. And so there's a powerful model there of how we can do more of that, focusing on those lands, those areas of our landscape that are most productive. Okay, so broad pictures, lots of excitement about this. I want to tell you that at this institution, Iowa State University, and in this college, Agriculture and Life Sciences, we are fully committed to all the topics that were touched on today. I know it's true all across this country and around the world that institutions like ours and lots of other kinds of institutions, and perhaps we're at an inflection point now where we can do more and really help to solve some of these problems, to push forward the capacity of our faculty, and even more important, the next generation of thinkers and doers, those would be our students, to think about these issues critically, to come up with new solutions, both incremental as well as jumpstart solutions to the kinds of problems that we face ecologically and in terms of our global environment, our global economy. So we're committed to that, working with the folks who have tuned in today. We're excited to do that. We are proposing out of this college, hopefully we'll develop into a new program to provide some additional seed funding and capacity for faculty all across this university to be able to move forward with carbon. Dr. Joe Coletti and I have talked about that of late. Joe Coletti, our Associate Dean for Research in the college, has even during this conversation today, pushed out a note to our colleagues around the campus saying, let's get together and figure out a way to further elevate the conversation, that Lisa and Robert have already provided us a platform to work from. So with that, I'll conclude. Thank you again for this wonderful morning and look forward to being part of all the next conversations that happen as well. Appreciate your attention so much.
Thank you so much, Dean Dan. It's so fantastic to hear our university leadership speaking in the way that you have for the college. And then, of course, President Winterstein and Provost Wickert this morning. And now I welcome the Endowed Dean of Engineering, Sam Easterling.
Well, thank you, Lisa. Can you hear me okay? So Lisa, can you hear me?
Yes, I can hear you.
Okay, thank you. Just wanted to double check. So thank you again, and as well as Robert and the entire committee for inviting me to just share a few remarks, and I will be brief. But for the broader work, thank you also for the broader work you've done putting the Carbon Removal Forum together. It's been a great event. Wonderful to see so many people attending. I've enjoyed listening to the conversation, the presentations, and the discussion. It really has been a great way to spend my morning. So my entire career has been committed to the land grant mission and the values it brings by creating and sharing, applying knowledge to make the world a better place. As some of you may know, I'm an alumnus of Iowa State University, and having received my doctorate degree in structural engineering in 1987, following graduation, I spent the next 32 years in various positions at Virginia Tech before proudly returning to Ames as Dean of the College of Engineering in 2019. One way we stay committed to the land grant mission is by having a robust research enterprise taking place in our college, across campus, and externally with our industry partners. We manage or are affiliated with more than 20 interdisciplinary centers and institutes, including the Bioeconomy Institute, the Nanovaccine Institute, and the Virtual Reality Application Center, just to name a few. Our Center for Industrial Research and Service, or CIRRUS, serves a major role across our state, helping to create jobs, improve manufacturing, and working with businesses of all sizes. The concepts of carbon reduction and removal from the atmosphere through agricultural activities is forward-thinking and beneficial to our society. I know you all plan to continue to engage with many stakeholders across universities, the state of Iowa, your own home state, and the country indeed. College of Engineering is in full support of this effort and really look forward to working together to find solutions based on scientific research and knowledge. There will certainly be many rich opportunities for engineers to contribute and be engaged in this important endeavor. We like challenges and helping to find solutions. So thank you for including our college in this forum. And we look forward and are committed to our collaborative work going forward. Thanks, Lisa.
Thanks so much, Dean Easterling. Please join me in thanking both of our deans for their fabulous comments that provide so much inspiration and show leadership within the university on these issues. So thank you. All right, well, I am the lucky person that gets to close this out. So let me get my PowerPoint up and loaded. There we go. Allie, can you see this?